So last time we used this technical lemma to prove that the Riemannian manifold is flat if and only if its curvature tensor vanishes identically. So now I would like to present a proof of this lemma. So let's suppose that x1, x2, xn are local coordinates centered at P, this point here, and we can suppose that the image of this coordinate map this coincides with C epsilon, which is defined to be the cube whose edges are have length equal to 2 epsilon. And we can do this by shrinking, if necessary, the domain of definition of this coordinate map, and we can also identify the coordinate, the domain of this coordinate map with C epsilon. So suppose that V is a vector in TPM. Then the first thing we will do is to consider the parallel transport along the x1 axis. Then the second step is to consider the parallel transport along the coordinate line parallel to the x2 axis and passing by each point of the x1 axis. So if you want to make a picture in 3 dimensions, you get this. So suppose that this is the x1 axis, this is the x2 axis, and this is the x3 axis. Let's use another cover. If we suppose that this is a vector V, then of course I'm assuming that the origin is the point P up to identification. Then first we consider the parallel transport along this axis. So for example, you get this, and then for each point of the axis x1, we construct the parallel transport of this vector field along each line parallel to this axis here, and we continue you can see the parallel transport along coordinate lines parallel to the x3 axis, passing by each point of the plane x1, x2. So this means that you have a vector field in this space. This construction produces a vector field V on at least on C epsilon. We have to prove that this is smooth and parallel. The fact that this is smooth is an easy consequence of the theorem about the smooth dependence of solutions of systems of linear ODE, because we know that the parallel transport equation can be written as a system of linear ODE. And this theorem must be applied several times because this vector field V has been obtained by considering the parallel transport several times. Instead, what about the parallelism of V? So we have to prove that this is a zero, and instead of proving this directly, we will use the linearity of the covariant differentiation in X over C infinity M. So we will prove only that this is zero for any I varying between 1 and n, because X can be written as xi delta I. So by construction, we have that this is true on the x1 axis, because we constructed V by considering the parallel transport along the x1 axis. We have that this is true on the x1, x2 plane for the same reason. And in general, we have that this is true on Mk, where Mk is defined by these identities: xk plus 1 equal xk plus 2 equal xn equals 0. So in order to prove that this is true, that is the vector field V is parallel, we have to show that this is 0 on Mk, and we will do this by induction. So for k equal 1, it is true because M1 is the x1 axis, and so we have that this is true. And we want to prove that this is true for k equal to n, because Mn is the cube. So let's suppose that star holds true for some k, and let's show that it is true for k plus 1. So let's observe that by construction this is true on Mk plus 1, and by inductive hypothesis for I not larger than k, we have that this is true on Mk, which is contained in Mk plus 1. Now we have to use the flatness criterion. So since the Lie bracket of delta k plus 1 delta k, sorry, delta I, this is 0, then the flatness criterion implies that this is 0, but on mk plus 1, but since this is 0, then we have that this is 0, that is this is parallel along the xk plus 1 curves starting on mk. But this is equal to 0, so since 0 is the unique parallel transport of 0, then we have that this is 0 on each xk plus 1 curve. And let's observe that every point of mk, which is a cube, sorry, which is a slice, is on one of these curves. So this implies that this is true on mk plus 1. I made a typo, sorry. And this is the end of the proof of the inductive step, and this means that V is parallel. The next important result is a theorem which shows that the curvature tensor measures also the failure of the identity between the identity map and the parallel transport around a small rectangle. So precisely, suppose that I is an open interval such that 0 belongs to I. Let gamma be a smooth one parameter family of curves in M, where M is a Riemannian manifold. Let P equal gamma 0, 0, X delta S gamma at 0, 0, Y delta T gamma 0, 0. Then let's denote by this symbol the parallel transport along the curve T gamma S1 T, and from time sorry, I made the typo. This must be T1. I'm sorry. From time T1 to T2, and then PS1 T1 S2 T1 This is the parallel transport along the curve which sends S to gamma ST1 from time S1 to time S2. Unfortunately, I have to erase. Then, for every Z in TPM, we have that the curvature tensor evaluated at XYZ. This is a limit as delta and epsilon tends to 0 of P delta 0, 0, 0 composed with P delta epsilon delta 0 composed with P 0 epsilon delta epsilon composed with P 0, 0, 0 epsilon of Z minus Z over delta epsilon. If you want, I can make a picture. So if this is the point P equal gamma 0, 0, and this is the vector V, what we are doing here is that first we consider the point transport along the curve gamma 0t for between times 0 and epsilon, 0 epsilon. So for example, if this is gamma 0 epsilon, I consider the point transport P0 0 0 epsilon, which is the operator which appear here. Then I follow the curve gamma s epsilon with the s varying between 0 and delta. So this point will be gamma delta epsilon, and this will be the parallel transport denoted by this symbol. It appears here. This is followed by the parallel transport along the curve gamma delta t with t varying between epsilon and 0. So this will be the point gamma delta 0, and this will be the parallel transport denoted by p delta 0 delta epsilon. It appears here. And now we can see the parallel transport along the curve gamma s0 with s varying between delta and 0, and this will be the parallel transport denoted by p delta 0 0 0. And sorry, this is a z. After composing these four parallel transport, we get, for example, this vector here, W, so Rxyz measures this limit, which is related to the difference between W and Z over delta epsilon when the denominator tends to 0. So how to prove this result? First of all, we consider the parallel transport of Z along this curve here, and we get Z0t. Then we consider the parallel transport along S gamma S t. So this means that first we move along this curve, and then we move along this curve. And we get a vector field which is smooth because of the theorem about the smooth dependence of the solution of a system of linear ODEs. And by construction we have two properties. dt of z0t equals 0 and dt, ds st equals 0. Now we use a proposition we proved in the recent past, showing the connection existing between the Riemann curvature tensor and the commutativity of second covariant derivative. Precisely in this case we get that Rx y z, this is ds dt c 0 0 minus dt ds z 0 0, but we have that this is 0, so this is 0, and the rest of the proof consists in proving that this is equal to limit as delta and epsilon tend to 0 of that complicated expression over delta epsilon. In order to do this, we use a theorem which shows how parallel transport determines the covariant derivative. Precisely, we replace this term by a covariant derivative, by an expression involving limit and the parallel transport. So precisely we have dt z as 0. According to this theorem, this is equal to limit as epsilon tending to 0 of PSS epsilon 0 of z s epsilon minus z s 0 divided by epsilon. We do something similar with ds dt z 0 0, ds dt z at 0 0. This is the limit as delta tends to 0 of p delta 0 0 0 of dt z delta 0 minus dt z 0, 0. So we have to replace this formula into this formula. The first time with the s replaced by delta. The second time with s replaced by 0. Unfortunately, I have to erase. And if we do this, we get that this is the limit as epsilon delta tends to 0 of a long expression where you have p delta 0, 0, 0 composed with p delta epsilon delta 0 of z delta epsilon minus p delta 0, 0, 0 z delta 0 minus p 0 epsilon 0, 0 z 0 epsilon plus c 0, 0. And now we have to simplify a bit this expression. Precisely, we want to write this term as the image of two applications of the parallel transport, and this term as this term. So this is possible because z by construction is parallel along this curve, and along this curve. So this means that p delta 0, 0, 0 z delta 0, which is this term here, this can be written as z 0, 0, this is z, p 0 epsilon 0, 0 z 0 epsilon, this is z 0, 0 again, this is this term here. Instead, what about this one? Z delta epsilon. This is the parallel transport of z 0 epsilon, and this one is the parallel transport of Z. So if I apply this, I get P 0 epsilon delta epsilon composed with this parallel transport acting on Z. And this is the end of the proof. And now I will present some properties of the curvature tensor. I will not provide the proofs of these properties because they are just long computations. So we have this proposition, which is about the symmetries of the curvature tensor. Precisely, we are considering the 0,4 curvature tensor. It satisfies the following formulas. Rm of W x y z, this is equal to negative Rm x w y z. So if you interchange the first two arguments, then you get a minus sign. A similar formula holds true if you interchange the positions of the last two entries. Instead, there is no change of sign if you interchange the position of the first and second pair of entries. Sorry, this is x. For any w, x, y, z in Q of m. The formula 4 is known as the algebraic Bianchi identity, or first Bianchi identity. In terms of components, then 1, which is this, is equivalent to write Rijkl equal to minus Rjikl. 2 is equivalent to write this. 3 is equivalent to Rijkl equal to this. And 4 is equivalent to write Rijkl plus Rjkil plus Rkijl equal to 0. Essentially, if you want to memorize the last formula, you have to keep L at the last position and considering permutation of ijk. So you get from ijk jki, and from jki you get kij. Another proposition, this is about the differential Bianchi identity, or second Bianchi identity. And it says that the covariant derivative of the 0 for tensor satisfies this formula. It's not difficult to be memorized. X and Y are the first two entries. Instead, for the remaining three entries, you consider a cyclic permutation. So from Z VW you have VWZ, and from VWZ you get WZV. Also, This formula can be written in terms of components. Precisely, you have R, I, J, K, L, semicolon M plus R, I, J, L, M, semicolon K plus R, I, J, M, K, semicolon L. This is 0. And I want to recall the formula for the covariant derivative of a tensor. We have that the covariant derivative of a tensor acting on L plus 1 vector fields. This is defined as the covariant derivative of this. And remember that the component of the tensor that you get by applying the covariant differentiation are denoted by the first index of the original tensor followed by a semicolon with an index for the new tensor. Also, this proof requires some computations that I will not present. Instead, what I want to do now is to talk about Ricci and scalar curvatures. So what is the Ricci curvature or Ricci tensor? It's a new tensor denoted by RC or RIC, and the definition is this: RC of xy, this is a trace of this map. From this formula you can also get the formula for the components of these sensors. They are denoted by Rij, and they are equal to Rkijk. So what we are doing here is that we raise one index of the 0,4 covariant, 0,4 curvature tensor, and in order to do this you have to multiply the metric by the components of the 0,4 curvature tensor and sum up. What is the scalar curvature? This is a function on M denoted by S or R. So S is the trace of the Ricci tensor, that is RII. This means that you have to raise one index here, and once again this is done by multiplying Rij with the metric, with the inverse of the metric, and summing up. Okay, we have now a lemma which says that the Ricci tensor is symmetric and it can be expressed in any of the following ways. Rij, this is Rkijk, but this is also Rikkj, but also minus Rkikj, but also minus Rikkjk. Let me check how much time I have. Okay. Now I want to introduce the traceless Ricci tensor. It is denoted by this symbol and it is defined by this formula. The reason why we call this tensor traceless tensor is that the following proposition holds. we have in fact that the trace is 0 and the Ricci tensor decomposes orthogonally as RC equal RC circle plus 1 over n as G. And the reason why we use this expression is that the norm squared of RC is the sum of the norm squared of RC circle plus 1 over n s squared. Or the expression orthogonal decomposition follows from the fact that the norm of RC behaves like the norm of vectors which admit orthogonal decomposition. So it is the sum of the square of the norm of the first element of the decomposition plus the square of the norm of the second element of the decomposition. At a first look, the second term could seem to be wrong, but this is the correct formula, because the norm of G squared is exactly n, so you don't have here 1 over n squared, but just 1 over n s squared. Okay, I want to give definition of Einstein metric. So we say that a metric is Einstein if the Ricci tensor is equal to lambda times G, where lambda is a constant. There are two interesting results about Einstein metrics. The first one is known as Schur lemma. I don't guarantee about the correctness of my pronunciation of this name. So suppose that mg is a connected Riemannian manifold of dimension at least equal to 3, such that the Ricci tensor satisfies this formula, where f is a smooth function. Surprisingly, we have that f must be a constant and G is an Einstein metric. A corollary of this proposition says that G is Einstein if and only if the traceless Ricci tensor is 0. I leave to you the proof of these two results. Okay, let me decide what to do now. Okay, let's talk about Schouten tensor and Weil tensor. In order to give definitions of this tensor, I had to introduce the Kulkarni-Nomizu product of two symmetric two tensors. So given H and K in sigma 2 V star, so this means that H and K are symmetric two tensors on the vector space V. Then we can define the Kulkarni-Nomizu product, denoted by this symbol, as follows. It is a 4 tensor, so we need 4 entries. So this is the formula. We have a formula for the components. So this formula gives the components of the product of H and K in terms of the components of H and K. So now we are ready to see the definition of the Schouten tensor. And the Weil tensor W equal Riemann tensor minus the product of P and G, that is Rm minus 1 over n minus 2, the product of the Ricci tensor Ng plus S over 2 n minus 1 and minus 2 G multiplied by itself. Clearly, they are defined only on manifolds of dimension at least 3. You can prove the following proposition. The trace of W is 0 and Rm equal W plus the product of P and G is an orthogonal decomposition. It is clear that the following corollary holds true. if, oh no, sorry, this is not so immediate to see. So if the dimension of M is 3, then W is 0, and we have that Rm can be written as the product of P and G. So this is a immediate consequence of this formula. That is Ricci tensor multiplied by G minus 1 over 4 S G multiplied by itself. What happens in dimension 2? If dimension of M is 2, then it is possible to prove that the Riemann tensor is just this, and the Ricci tensor is just 1/2 SG. Maybe it's a good idea to stop here. I want just to present one last proposition. Which is about the Ricci decomposition of the curvature tensor. So suppose that dimension of M is at least 3, then the 0 for curvature tensor can be decomposed as follows. Rm equal W plus this term 1 over n minus 2 traceless Ricci tensor multiplied by G plus one over 2n n minus 1 S G multiplied by itself. And you have a formula for the square of the norm of this tensor. Actually, you have two formulas. The first one is an easy consequence of this one. Just write the sum of the square of the norms of each summand. You can do this because the composition is orthogonal, but after simplification you can write the sum, this square of the norm as square of the norm of W plus 4 over n minus 2 of the square of the norm of the traces of each tensor plus 2 over n times n minus 1 s squared. Okay, now it's time to stop. Thank you.